signal subspace and noise subspace. And of course, the signal subspace contains also noise. So how do we do that separation? How do we find the signal subspace? We take the correlation matrix of the desired signal, Rx, which is L by L matrix, and then we find the eigenvectors and eigenvalues. So the matrix Qx, we can diagonalize the matrix Rx. So if we diagonalize this matrix Rx using eigenvectors and eigenvalues, the columns in the matrix Qx are the eigenvectors, and the diagonal along in the matrix lambda x contains the eigenvalues. So if we know that the rank of Rx is lower than L, so the rank is P, which is lower than L, we know that some of the eigenvalues here in lambda are 0. So we have P non-zero eigenvalues. So what we need to know, we can take this matrix and order the eigenvectors according to decreasing order of the eigenvalues. And we know that any signal, any vector, actually any vector, y or x or v, any vector of length L, we can write it as a superposition of these vectors. Why? Because these vectors span all vectors of length L. They span the whole space. But if the rank of Rx is only P, which is smaller than L, it means that we can take only P eigenvectors, and these P eigenvectors with the eigenvalues which are different than 0 span the signal subspace. So while any signal, y for example, vector y, and for anything, actually any vector, any general vector of length L can be written as a superposition from I equals to 1 to L outside, like this. Okay, thank you. Okay, so I hope that you could hear what I said before, or maybe I need to repeat. Okay, okay. So what will be the coefficient? It's a superposition of these vectors. What is the coefficient here? Exactly, exactly. So it's y transpose q x I. Okay, so these are coefficients. These are numbers. So these numbers multiply with this. But if we take a vector of the desired signal, so we know that a vector of the desired signal, we don't need all these vectors. It's sufficient to take only the vectors that correspond to eigenvalues which are larger than 0 or different than 0. So we have here I from 1 to p q x I x t transpose q x I. Okay, these are the coefficients. Okay, and we know that actually this inner product, we know but yesterday they replaced the batteries, no? Or maybe day before yesterday. Okay, I don't know why it turns off. Anyway, so that's why the signal subspace is spanned by the first eigenvectors, the first p eigenvectors that correspond to eigenvalues which are different than 0. What about the eigenvalues? What do you think? Can we? It shows like the battery is empty. Yeah, it shows the battery level. Shows like it's empty. Okay, because the video needs a microphone. We'll wait a few minutes. So it turns off. To take something from your background. Some people have background in radar, some sonar, some signal processing, and so on. So think about single channel
signal enhancement. The fact that you have noisy measurements of a signal and you want to enhance, to estimate the desired signal that is contained. So we assume certain models in the examples in that panel. Try to take something for your research, or if you don't have something relevant, try to think about, you can read in the literature, okay, about something relevant. Signal enhancement, you go around it. And I don't ask you to read like journal papers publication to you, but just to think about the problem, how the problem is formulated, and how does it compare to what we live here, what do we have since we studied single-channel signal enhancement. How can we use what we studied and what is missing? Because I gave you some insight, what is missing. For example, in the example that we saw here, we need our X and our Y, or our X and our B, which is not easy. So just think, even without solving the problem, think about how the real problem in practice can be addressed or formulated, what is missing, what do they need additional information, and so on. If you don't have something relevant to your research, think about radar. We talked about radar, sonar. If you like cosmology, also interesting, the small difficult underwater signals, propagation, and so on. Read about anything that interests you that is related to signal enhancement, and see how the problem is formulated. Okay? Try to understand the problem from the different disciplines. And if you like, some of you, okay, prepare one slide or two slides, whatever. Talk about this problem in front of the class. Okay? Let me know, we will have to give time. So it can be relevant to signal enhancement in the time domain. We will study also in the frequency domain or multi-channel, whatever you like. Okay? It will be nice. And you can give some time to people to talk in front of the class about this problem that is there. We're waiting for the battery, and you can think. Do you have questions? Yes. Yes, it's always true. You know, there's no free lunch these days. When we try to achieve something, it comes at the cost of other things. And so if you take different methods, usually any method that you choose for signal enhancement, it combines some trade-offs. So sometimes the trade-offs comes between noise reduction and signal distortion. Sometimes it requires more computational complexity, sometimes more memory. For example, using deep learning. Oh, it works.
Okay, thank you. Okay, ready for a question? If P is smaller, can we reduce more noise or less noise? What is the effect of P? What? Exactly. So if P is smaller, it means that the noise-only subspace is larger. So we have more noise to reduce without any distortion. So with the MVDR, we will see that if P is smaller, it means that the signal is contained in a smaller subspace. We can reduce more noise without distorting the signal. What? If P is L. Good question. If P is L, what does it mean? That the MVDR, what will happen with the MVDR? No noise reduction. It doesn't do anything. Actually, Z will be equal to Y. No noise reduction. Why? Because the constraint is no distortion of the signal. And if P equals to L, we don't have any noise to reduce without distorting the signal. If what? With Wiener filter, yes, but the Wiener filter introduces distortion. So if you allow distortion, you can always reduce noise. And with the trade-off, you have a trade-off. If it reduces more noise than Wiener or less. And this will come how much distortion you introduce. Okay? But the MVDR, it doesn't allow any distortion. That's why we need some subspace of noise only. It's just like with the Fourier transform. If the signal is present in all frequencies, then you cannot reduce noise. Okay? But I will give you also some interesting thought. When we say about here, we talk about the signal, and maybe the signal is stationary or not. But if the signal is not stationary, it means that, suppose that, for example, speech signal, if you take the Fourier transform of a long speech signal, long, it can be a few seconds of speech, you will identify that the signal is present in all frequencies. Okay? So then you think, okay, then MVDR will not be able to reduce any noise. Yes? So MVDR filter will not be able to reduce any noise. That's why we need other filters that put some trade-off between noise reduction and distortion. So I say, I can tell you that even MVDR, single channel speech enhancement, can reduce noise. What do you think? How this can happen? How can MVDR reduce noise even for speech signal that is contained in all frequencies? What do you think? No, I said single channel. Multi-channel, we come to that. I agree with you. Multi-channel, we have more possibilities. But even single channel, it can reduce noise. What? Exactly. Okay, by windowing. So, actually, I wanted two answers. Okay? Windowing, that's a good... okay, because you started with this, I will talk about this, this solution. Windowing. Okay, so if we window the speech signal to intervals by windows, intervals of a few tens of milliseconds, 20 milliseconds, 30 milliseconds, 50 milliseconds. During this interval, we have just a small portion of the speech phoneme or some part of the speech signal. And in that part, it doesn't span all frequencies. So you can see that speech signal is contained in some of the frequencies. So we can remove this noise in other frequency without any distortion. And then for each window, we can remove noise from other frequencies. This is one thing. Okay? So it's a very good answer by windowing. Do you think about other thing? Not speech, any signal. Suppose that the signal is contained in all frequencies and I use MVDR. Still, I can remove some of the noise. How? For stationary signal, not speech, any signal. Signal that contains all frequencies. And still, I can remove noise without any distortion. How can that happen? Okay? So it's, if we think about it, I didn't say that we need to implement MVDR in the Fourier transform. So maybe it contains all frequencies. But maybe the eigenvectors, the first eigenvectors, so if I find the eigenvectors and eigenvalues, I see that the rank of Rx is P, which is lower than L, even though it contains all the frequencies. You see, the eigenvectors, even lower rank than L, low rank of Rx, maybe the signal is contained in all frequencies, but when I span it using the eigenvectors, I need only P eigenvectors. Okay? Do you know how we call this transform? This is very useful for signal processing. Many times for images and so on and other signals. So this is called Karhunen-Loew transform. Okay? If you're not familiar, you can read about it. Karhunen-Loew transform. Which means that instead of Fourier transform, which you are familiar, we transform the signal. This is the transform of the signal, or representation of the signal using the Karhunen-Loew transform, using the eigenvectors of the correlation matrix. Okay? So even though the signal is contained in all frequency using the Fourier transform, it doesn't mean that is lower rank or can be represented by a smaller number of eigenvectors using the Karhunen-Loew transform. Because here we use the Karhunen-Loew transform. Okay, so in the Fourier transform, maybe it's full rank, like or it's not full rank, or maybe we need all the frequencies. We need to go from I to L, even here, from I to L, using not the eigenvectors of the correlation matrix of X, but if we use the space, okay, the vector subspace of the Fourier transform. So if we take the Fourier matrix, the Fourier transform matrix, L by L, and we take the columns of the Fourier transform matrix, so maybe we need all the vectors to represent a signal of X. That's why we move to the Karhunen-Loew, because here it depends on the rank. Okay, if something is unfamiliar or you want to ask questions, please ask questions. Okay? Okay. Any questions? Okay, so let's continue. So we split this matrix into two parts, the signal subspace, which is sometimes we call it signal plus noise, and to the null subspace. Sometimes we call it null subspace or noise subspace. Null subspace, it means that there is no signal over there. Noise subspace. Okay, so these terms are equivalent, are the same terms. So this matrix, the size is L by P, and this matrix is L by L minus P. So actually we can write, you see, we can write any vector of size of length L of X. We can use, instead of the full matrix, full representation of the signal, we can use only the first P eigenvectors. It's the same, because outside that we don't have any signal. Okay. So we say what is the distortionless constraint? Because what we need to do with the MVDR, we minimize the noise at the output, This is the estimate. We want here that to minimize the noise because it contains noise plus filter desired. So we want to minimize the noise while not distorting the desired signal. So we can write the distortionless constraint in such a way that H transpose, this is the distortionless constraint. H transpose X equals to X, right? This is the distortionless. Why? Because how do we obtain this? We obtained it as H transpose Y. And this contains two parts. H transpose X plus H transpose V. So we want to minimize the variance of this. So the variance of the residual noise. But we want that this will be equal exactly to xt, which means, this means that the filtered desired part in the estimate is not distorted. And this is the residual noise. Okay, and we want to minimize this. So what is the constraint? That H transpose X equals to X. So it's equivalent to say that H transpose, that we apply H transpose to any Q xi from I to P remains the same. It's the same. See? So it will be like if you take H transpose that we apply it to the matrix Qx prime. Qx prime contains only the first P eigenvectors. Okay? So it's just like taking the vector. This is vector 1 and all zeros. Okay? You take it like this. So it's the same as taking I and 1 and all zeros, and you apply it to the same matrix. So let's think about this vector, okay? So how many constraints do we have here? Here, in the equation 62. How many constraints? How many equations? This is a vector, right? What is the length of this vector? What? What is the size of this vector? No, not L, P, P, okay? If it was L, it was not good. Then, because if we take subspace of, if we take any subspace with L, with a basis of L vectors, and we apply HT to all these L vectors, and we want them to be distortionless, then it means that we cannot reduce any noise. Here, instead of applying it to any X, any signal X, we apply it only to P eigenvectors. Okay? If I write it here in a matrix form, actually we have P equations. P equations, it means that if we apply H to any eigenvector from 1 to P, the first eigenvector, to any eigenvectors from I to P, we apply it, so it's distortionless, remains the same. Okay? You see it? This equation 62 is just like writing that H transpose Q xi equals to Q xi for all I equals 1 to P. So here we have P constraints. The constraint is on the signal subspace, and the signal subspace is spanned by Q eigenvectors. So using these constraints. So instead of saying that H transpose X is equal to X to any X, any possible X, we need to apply it for all eigenvectors from 1 to L if we don't know the rank of X, the signal subspace. So just like the Fourier transform, so you take the representation of the Fourier matrix, Fourier transform matrix. So it will be any L vectors that span any vector of length L. But then it's enough that we have only P constraints, which is less than L. That's why we can suppress some noise. Okay? So our problem of the MVDR, you see, this is a very nice problem. To minimize the variance of the noise, to minimize this part, the variance of this part. Subject to P constraints. These are P constraints. And so if we don't want to have any distortion in this signal subspace, we can remove it. So we have this solution, okay, like this. So actually, we can check if this constraint is satisfied using this solution. This is the first thing to do. When you see a solution, first try to find the solution to prove that it's like this. But also, we can check that if we take this constraint, if this solution is satisfied, we can put HMVDR here and to see if this is satisfied, which is very easy to see. Okay? Take the transpose here and multiply it with QX prime transpose from here. So this cancels, and then you get exactly this. Straightforward to see. But also, what it means, you need to understand what it means. That in this signal subspace, the filter doesn't do anything. So all the coefficients which are represented, all the part of the signal that is represented in the first from 1 to P, we don't do anything with the filter H. It doesn't touch them. It keeps them intact, like this. And then it reduces the noise in the remaining subspace. So it actually, the easiest way to reduce the noise is to put nulls, zeros, in the other coefficients. Very easy. Okay, let's continue. So we see that the MVDR can also be expressed differently, which is very nice, because if we compare this solution, you see this solution, we see QX. By the way, to find, we assume that we know information. What kind of information we know? Still here, we know the information Rx. You see? So along all this single channel signal enhancement, we assume that we know Rx and Rv. That's why we know the eigenvectors that diagonalize Rx. Okay, and instead of using Rv and Rx, we can change it using Ry and Rx. So it's Ry and Rx, the eigenvectors are from here. So instead of using Rv, which we need to estimate it based on the noise, here in this expression, we see that once we know the eigenvectors that diagonalize Rx, here, if we use something adaptive, for example, we use the correlation matrix of the measurements, because sometimes it's easier to find the correlation matrix of the measurements based on received data. By the way, if we don't know the eigenvectors of Rx, just like what you said before, okay? Because it's very difficult to find for each interval of window the Rx, and then to find the eigenvectors that diagonalize this part of the signal. Think about it. Suppose that I have non-stationary signal like speech. For each interval of a few tenths of milliseconds, I need to find Rx, and then I need to find the matrix Q, the eigenvectors that diagonalize Rx and that window, and then I need to represent the signal and then remove the null subspace and so on, which is difficult. It's time-consuming, high computational complexity, and so on. Instead of that, what do you think if I will just use the Fourier transform on that interval, and that window? Makes sense. Because Fourier transform, I don't need to change it. I don't need to estimate Rx in order to find eigenvectors. And also, I have a fast algorithm to find the f on that window, and log n. So the computational complexity will be lower. Whereas to find the eigenvectors of a matrix is high computational complexity. And also the representation using that, the coefficients, also it's high complexity. That's why window Fourier transform or short time Fourier transform is very useful to processing non-stationary signal, because it's much more efficient computationally instead of finding on each interval the Karhunen-Loew transform. But the reason behind it, okay, and the understanding is very similar. Okay? That's why we use short-time Fourier transform for many non-stationary signals. Or another transform, can be discrete cosine transform or other transform, because we want to sacrifice the performance by reducing the computational complexity using existing fast transforms. Okay. We can, in case that we have white noise, by the way, if we take white noise, then RV will be diagonal, like this. Why? Because any two samples of the vector V are uncorrelated, which means that this matrix is diagonal. So in this case, the MVDR reduces to this expression. It's just a special case. What we see here, so you can think that because that the MVDR filter reduces less noise, maybe it also the output SNR can be, in some cases, lower than input SNR. But actually, I can convince you that this is very easy to prove. Why do you think it's easy to prove? This is very easy to prove. Even by intuition, what do you think? How do I know that the output SNR with the MVDR filter is always larger than the input SNR? It's much easier than the other filters. Why? Don't be shy. Okay. What? The estimate. It has two components, X and residual noise. X is the same. The noise will be smaller than the input. So this ratio, the variance of this ratio, is always smaller. This ratio is with the output, always the ratio will be higher than the input, or at least equal to the input SNR. So this is very easy. With the Wiener filter or the trade-off filter, it's not so obvious, because we reduce this, we have distortion and with noise reduction. But with the MVDR, we don't have distortion. So the portion of the part of the signal remains the same. And this becomes smaller. So the ratio becomes at least larger or not smaller. Okay? Even easier. So this is nice. So therefore we have also this property also for the MVDR, which is nice. That's why I don't show proof, but because it's easy to show it. Okay? Very easy. What I said before, so it's straightforward. Example. Let's see this example. So suppose that the signal contains superposition of a few cosine functions like this. And the amplitude of each cosine is different amplitude and different frequency and different phase. Okay? By the way, because it's a cosine, if I take a certain length of the signal, the eigenvectors will be very similar, in general, very similar to the Fourier transform. Okay? Either Fourier transform or some representation. Of course, it's not the Fourier transform, because the Fourier transform is complex. It contains complex. But it will be very similar. If I take the eigenvectors are different cosine. If you take a matrix Rx or something like that, the eigenvectors will look like cosine vectors with different frequencies. Very similar. Not exactly, but very similar. But it's not like the Fourier transform. It may be like cosine transform. Because the eigenvectors are real. All values are real numbers. So if I take this signal, and it contains k frequencies, what do you think? How many eigenvectors do I need to represent such signal in the signal subspace? What? K? 1? K? Let's think about it. The phase here is random. So your answer that we need K, it's a good answer, but it's not sufficient. What? 2 times K. Why? Exactly. We need the cosine and the sine. Or we need the cosine or the minus frequency or whatever. But in order to represent cosine something with a random phase, we need the cosine and the sine. So if we take any signal like this, so any vector of length L, we have L eigenvectors. L divided by 2, half of them are actually cosine of the frequencies, and half of them the sine of the frequencies. And then any signal of length L can be represented as summation of cosine and sine. So for each frequency, we need 2 eigenvectors from the cosine and the sine of those frequencies. So I agree. We need 2L eigenvectors. So the rank of this vector, if we take vector of length L samples, we need 2K eigenvectors to represent signal like this. Okay, and suppose that we have also here white Gaussian noise. So white Gaussian noise, we can compute Rx. first we know that RV is diagonal with sigma V squared IL, and Rx from the model looks like this. These are the elements of Rx. And if you check, the rank of Rx will be 2K. And suppose what we can do is we take the eigenvectors with the positive eigenvalues, and we take these 2K eigenvectors, and then we can represent these any signal of x by these 2K eigenvectors. So suppose for certain, in this example, suppose that AK, all of them the same amplitude, 0.5, and the frequencies are different. Okay, and you need to use different frequencies for any signal. So it's 0.05 multiplied with K, so multiplication of K by 0.05. So you need to check that for the largest K is still smaller than half. So Nyquist frequency, it is satisfied. The Nyquist is smaller than the Nyquist frequency, so we don't have any aliasing. And then we take L equals to 30, and we want to see how K, what is the effect of changing K on the noise reduction. How K, if we take the MVDR filter, what is the effect of K on the signal distortion? What? No effect, right? Why no effect? There's no effect. K doesn't change the distortion because the distortion is 0. MVDR, obviously, 0 distortion. So K doesn't affect the distortion, but it does affect the noise reduction. Because if K is larger, then the signal subspace increases. The signal subspace, the rank is 2K, so it increases. So it means that we have less noise to suppress. In frequencies, other frequencies, okay? Because it reduces noise where signal is not present. So we can see this. So in this, we see the gain in SNR as function of input SNR, the MSC, the noise reduction factor, and the distortion. So you see the distortion, this desired signal reduction factor is 0 dB. No distortion, no matter what is K. So we have here different plots for different K. K equals to 1, 2, 4, and 8. 1, 2, 4, 8. So we see that when we increase K from 1 to 2, or we further increase it to 4 or 8, if we increase K, what happens to the noise reduction factor? Decreases. So because we have less noise to suppress without distorting the signal. So K increases, noise reduction decreases. Distortion, no distortion. Doesn't affect distortion. What happened with the gain in SNR? The gain in SNR necessarily is decreased because X remains the same. We reduce less noise, so the output SNR decreases. What happens with the MSE? The mean squared error. So the mean squared error, it means that if we increase, we have less noise to decrease, the MSE increases. Because the MSE comes only from this part, from the residual noise. If we have more noise, the MSE increases. Any questions? Okay. So here we see a very nice observation, because we saw the expression for the MVDR filter. So it's very nice to see how the MVDR and the trade-off filters, how can we express them when we represent the signal using the eigenvectors of Rx. Okay, we can do that. We showed certain expressions for the Wiener filter and the trade-off filter. But we can also express them in this space, of the space that's spanned by the eigenvectors of Rx. So if we write them, we can express Wiener. By the way, it's very nice how to use that, Woodbury's identity and so on. So the derivation is also nice. For people that want to practice the mathematics, I recommend to follow these derivations. And I can also give you the solutions and how it's derived. But the result here, the Wiener filter, can be represented in this space using this. So what is the difference between Wiener filter and the MVDR? This part. You see this part. So if with the Wiener filter we didn't have this part, and then when we applied the MVDR, when we applied it to the vectors in Qx prime, which are the first eigenvectors, we didn't have any distortion. Here we add this matrix, and because of that, application of the Wiener filter to the vectors in Qx prime will not reproduce these vectors. We will distort. It will be lower. So it will reduce the signal. So we will not get the original signal in this part. We will get something lower, which is exactly the Wiener filter. The Wiener filter, what it takes in the signal subspace, it suppresses the signal according to the signal-to-noise ratio. But it's very beautiful to see the relation. It's only this matrix. If we remove it, so it's actually the MVDR. What do you think now? If to put the trade-off filter, what do we need to do? I remind you, the trade-off is similar to the Wiener, but we need to change RV with mu RV. But you need to be careful, just like I said, if you have different expressions with subtraction and so on. So if you add here mu, like here, you add mu here, so you get the trade-off filter. Okay? So we see the relations between different methods, different filters. We can represent them using different eigenvectors. I think you deserve tea now, or shall to continue? Now it's the tea break? Okay, so we have 10 minutes or